In this video, I'll explain the concepts of linear dimension in transformer, how variation of linear dimensions leads to changes in iron losses and kVA rating, and also no load current, magnetizing current, etc. So first, this question was asked in the year 1992. The question is, two transformers of the same type using the same grade of iron and conductor materials are designed to work at same flux and current density, but the linear dimension of one transformer is two times the other. So we have to find the ratio of kVA rating of two transformers. So first and foremost, we should know that flux and current densities are same. That is, flux density Bm and current density, that is J, are constant, are same. So we know that by formula Vm is equals to flux upon area, because density is known as quantity divided by area, and similarly current density is given as current upon area. Since flux density and current density are constant, flux will be directly proportional to area, and also current will be directly proportional to area. And now we know the EMF equation of transformer is given by E is equals to 4.44 N F phi m. And by this equation, we can see that EMF will be directly proportional to flux. Since EMF is directly proportional to flux, and here we have seen in equation 1, flux is directly proportional to area. So we can write EMF will be directly proportional to area. Let this be equation number 3. I will explain more about this in the end of the video because it will ruin this question. Or actually, we should be finding ratio of kVA rating of transformer 1 and transformer 2. We know that kVA is basically E into I, and here E is also directly proportional to A, and I is also directly proportional to A. That means our kVA will be directly proportional to area square. In the question, they have told that linear dimension of transformer 1 is equal to 2 times the linear dimension of transformer 2. Let T1 be the linear dimension of transformer 1, which is actually 2 times the T2. Let T2 be the linear dimension of transformer 2, and we know the formula for area of any figure, that will be length into breadth, or we can say dimension into dimension. Here we can also say linear dimension into linear dimension, or linear dimension square. That means area is equals to square of linear dimension. And if we square this equation, let this be equation 4, and we will square equation 4. So we will have T1 square is equal to 4 times T2 square. That means we have seen that area from 5, we have seen that area is equals to square of linear dimension. So now we have area of transformer 1, which is 4 times area of transformer 2. Let this be equation 6, and from 6, kVA 1 by kVA 2 equals area 1 by area 2 whole square. That means here we can substitute value of A2 in this equation, and we can write 4 times A2 divided by A2. Don't forget, we have a square here. So that brings us to the answer that ratio of kVA1 by kVA2 will be 4 square, that is 16. So that brings us to the answer A. As I had told that I will be explaining the relation of linear dimensions with other major components. So now first I will give the relation of every parameter. kVA is directly proportional to linear dimension to the power of 4. Losses are directly proportional to cube of linear dimension. Voltage rating is directly proportional to square of linear dimension. Current rating is also directly proportional to square of linear dimension. No load current is directly proportional to linear dimension. Magnetizing current is also directly proportional to linear dimension. Similarly, core loss component current is also directly proportional to linear dimension. Now, I will justify few of them on how this is derived. In the previous question, we saw that kVA of first transformer is 16 times kVA of second transformer, where we actually took linear dimension of first transformer is 2 times linear dimension of second transformer. It can be said that 2 power 16 can be written as 2 power 4 times kVA, and if linear dimension is k times linear dimension of second transformer, that means kVA will be directly proportional to k times power 4. This I have written in the equation number 1. And we also saw E will be directly proportional to area, and we know that area is actually length square. That brings us that E will be directly proportional to area square, and that similarly goes to current as well. Now that brings us the no load current. We know that E is directly proportional to flux. And we know flux is actually mmf upon reluctance. So here S is reluctance, not the kVA rating. We actually know that a resistance is actually rho L by A. Similarly, you might be knowing that reluctance is actually L by mu A. By substituting this in the flux equation, we have mmf mu A upon L. And we also know mmf is basically N into I. So that brings us flux as NIA, and we can write it as E is directly proportional to I naught A by L, because we know E and flux are directly proportional. And we also know that E will be directly proportional to area, because now with that note we can write area as proportional to I naught area upon L. Since gets cancelled, and I naught will be directly proportional to L, or this is what I have written there. So that brings us, basically this column is most important because some questions are asked directly based on this.